All right. Well, welcome back, folks. I know that it was kind of a short break between our exam last week and what we're going to be doing uh, from here on till we meet again on I think it's January 5th when we resume school. But I know I talked about this. I'd mentioned then that we will be working on. And I'm sorry. Let me go ahead and set my timer here. Let me explain why in just a moment. Um, but we do need to get caught up because of the schedule that we had over the fall semester and not meeting on Wednesdays. We've fallen behind, and so I think we need to be able to utilize the time that we have here to try to get caught up. And so, I'll be making these videos. I'll be putting out these videos for you. They are required that you watch these videos, but I won't make them due until the end of the first week of school. So I think we start on a Tuesday, Wednesday, I think it is. So that may be the 5th. And then the assignments, these Edpuzzle assignments, will be due that Friday. So we'll give you some time, but please don't put off watching these videos until then. Because what I'll do then is when we start up again, when we meet again on January 5th, I'm going to pick up right where the videos leave off, and so not where we left off at the end of last semester, not where we left off last Friday or a couple Fridays ago. But I will be picking up where we leave off from these videos here. And so that means that I'm going to try to get through chapter 14. So over these next few videos, I'll be watching them. So I'll try to get finished with chapter 14. That means that when we meet back in January 5th, I will start chapter 15. And so the first exam, after we get back, the first exam, we'll cover chapter 14. I'll give you more details on that as when we meet again on how that exam will proceed. And so, so your first exam will be on chapter 14, and chapter 14 will be covered through these videos. But I do want to give you some flexibility in how you watch these videos. And so watch it when you can, but try to watch one video a day if you can. I'll be putting out these videos. Hopefully I'll try to get them out before the afternoon of that day. And so, so try to watch the videos, watch them at your own pace, answer the questions, please, and submit your answers, and then be ready and have them watched by the time we meet in the new semester. Okay, what I'll try to do is I'll try to keep these videos around the same time that we would spend if we were to meet in person. So it'd be a 45-minute video, and that would include then the questions and hopefully some time that I would give you to answer the questions. And so I'm going to try to keep it about 45 minutes. But again, you don't want to watch these videos all at one time. Okay, and so please make sure you watch these videos and make sure you pace yourself, spread the videos out. I know that they're not probably the most exciting videos to watch. There's probably much more, many more exciting things you can do besides watch videos of Mr. N discussing AP chemistry. I get jazzed about this stuff. I know that you folks aren't the same. And so, try to pace yourself. Don't binge. Do not binge these videos. Okay. I highly recommend that you do not binge these videos. Okay. All right. So with that said, then, like I said, I'm going to try to keep these videos short or relatively short, about 45 minutes. I'm going to use this time here to get through chapter 14. I'll be posting videos during the week. And so that way, then, the weekends, you don't have to worry about it. Okay. So please make sure you watch these videos. Okay. So let's go ahead then. Let's pick up where we left off with from last Friday. We were talking about Le Chatelier's principle, and Le Chatelier's principle, remember, is a way that we can examine equilibrium of any process without doing any calculations. The whole idea behind Le Chatelier's principle is to obtain then a qualitative measure or a qualitative assessment of the direction that a process will take, the direction that the process will take in order to reestablish equilibrium. So Le Chatelier's principle is our way of quickly, and hopefully it'll be quickly, and we'll talk about how we can do it in just a moment, how we can quickly analyze a set of circumstances and determine then the direction equilibrium will take, if it takes any at all, in order to for that process to reestablish the equilibrium that's in. Okay, all right. So we left off at the Haber process. So we were talking about the Haber process here. We were talking about how with this Haber process, oh, I'm sorry. Let me share my video, share my screen. It's probably going to be important for you. Okay. So we left off with the discussion of this Haber process here. So let me go ahead and share that with you. Okay, there we go. And what we talked about then was, remember that there are certain conditions of the Haber process that is required in order for it to run well. Okay. All right. So first of all, we see then we see then that temperature and pressure are given it to us on this table here. We see then what we're given here is the percentage of ammonia that's produced. Okay, so this is the percentage of ammonia that is produced during the course of the Haber process. And let me go ahead and write out the reaction here for you. Okay, so when we talk about the Haber process, we were discussing a reaction that involves, remember, the reaction of gaseous nitrogen reacting with gaseous hydrogen, okay, to produce then ammonia also in the gaseous state. Now I want to emphasize here that these are all gases. This is going to be important in our discussion in just a moment about how pressure will affect this. But if you notice then, I'm sorry, in a 1:3:2 ratio. Okay, so this I'll be using the Haber process moving forward. I'll be using this to discuss Le Chatelier's principle. So please make sure you keep this in mind. Okay, and so we were able to define then the equilibrium constant for this reaction. We've been using this reaction quite a bit. So we were able to define the equilibrium constant for this reaction either in terms of concentrations or in terms of pressure. And so we'll talk about that in turn as well. Okay. All right. So let's take a look at this here. What we were given then is we were given the percent of ammonia that's produced at different temperatures and at different pressures. And if you notice then, if we take a look at this, that as we increase the pressure, as pressure increases, I'm sorry, as temperature increases as we go down, we notice then something happening here, and that is the amount of ammonia that's produced. That is the amount of product that's produced is it drops as the temperature goes up. The amount of product is going down. Excuse me. You get a less and less product. What does that mean about equilibrium? This is where I wanted to pick up with this, because I kind of felt that we went through this fairly quickly last Friday. Okay. The amount of, understand this, the amount of product is, the amount of ammonia produced is dropping. That means if we take a look at this equilibrium, we're going to have less and less of the ammonia being produced here. What does that mean then? That means then more and more of the reactants are being produced. So as the temperature increases, I hope you recognize that the equilibrium starts to shift back towards the reactant. Okay, that's what this information gives us right here. It tells us then that as the temperature goes up, as the temperature increases, the amount of ammonia decreases, the amount of product decreases. Now, if the amount of product decreases, the reaction has to shift in one way or another. The equilibrium has changed. Okay? The equilibrium position has changed. And so therefore, we have now more and more reactants. Okay? So the equilibrium is shifting back towards reactants. So we see that's what's happening when we increase the temperature. Okay. Now, let's take a look at what happens when with the pressure. And this is true then for all of these given pressures. So whether it's at 300, 400, or 500, as you increase the temperature, the amount of ammonia produced drops. That means that the temperature affects the equilibrium. Equilibrium as well as the equilibrium position. Okay? So if we take a look at what happens then as we increase the pressure now. So as we increase the pressure, so as pressure increases, what we notice then is that the amount of ammonia being produced increases. Okay, so as we increase the pressure on the whole thing, as we increase the pressure on the reaction itself, on this process itself, we see then that the amount of ammonia produced is going to increase, which is the opposite of what we see with the temperature. Okay, so what we notice then that as we increase the pressure, the reaction is shifting towards the right. As we increase the temperature, the reaction shifts towards the left. And I'll go ahead and write this in. Then we see then a shift towards the left, as we increase the, let's go and write this in. So as the temperature increases, we see a shift to the left, which means that we are seeing a shift towards the reactants. As the pressure goes up, we see a shift to the right. which means that we are getting more product. So we are shifting the equilibrium based upon the temperature and the pressure that we run this reaction. And so that means that with the, if you take a look at this, if we want the reaction to form more ammonia, if we want more ammonia out of this, we see then that we should run this reaction at a fairly low temperature, but fairly high pressure. Now there's a limit to, and so you might say then, well, look, if that's the case, why don't we just keep dropping the temperature for more and more? A higher pressure, lower temperature. Well, that doesn't really quite work, because in practice, then what happens is if you drop the temperature too much, the kinetics of it, the reaction will run so slow, you won't get the product in a timely manner. So there is a kinetic element to this that we also have to consider. Okay, so we won't talk about the kinetics of a reaction until chapter 12. Okay, so understand then we're only focusing on equilibrium here. And so the reason why we can't drop the temperature all the way down to 0, for example, and still keep the pressure high is because then the temperature the reaction runs very, very slowly. Okay. All right. Okay. So, with that said, in terms of questions, if you have any questions, please make sure then you write them down. And then what we'll do is when we meet, and again, before before the exam, chapter 14, which will include a little bit of the Chartier's principle, you can ask the questions as well. Or if you would like, you can email me the questions. I will, if the questions are pretty straightforward, I will go ahead and email you back an answer. If they're not too straightforward, I may ask you to hold on to that question until we meet in person come January 5th. Okay. All right. So let's continue on then. Let me go ahead and save this. And I'll continue to post these slides also on Google Classroom. So please make sure you check that as well. Okay. So I'll go ahead and post these slides for you. But let's go ahead then and let's take a look at what happens here. So with equilibrium. So what I have here for you then is a table in which I have listed for you the Kp, the value for Kp. So the equilibrium constant based on partial pressures. So there it is. These are the values for Kp and the corresponding temperatures here in degrees Celsius. Okay. First thing I want you to notice then, and I hope you've noticed this already, that as we increase the temperature, and we've already pointed this out, the equilibrium constant will change. And if you notice here, as the temperature increases, the equilibrium constant gets smaller and smaller. Okay. And so remember, let me go ahead and let me point this out to you again. Okay. In the reaction that we saw previously, okay, we saw then that as we increase the temperature, the percentage of ammonia decreases. So what you're going to notice here, as we increase the temperature, the percentage of ammonia also decreases. So you see then a smaller and smaller amount. Sorry, my whiteboard's acting up. A smaller and smaller amount of ammonia being produced. Okay, that means then, what does that mean for us? Okay, and so let's make sure you keep that in mind. What that means for us, like I pointed out to you before, okay, that means for us then, and let me get this out of the way here, is that as the temperature increases, okay, we see then that Kp decreases. Okay, so this is what we see here. So if the percentage of ammonia decreases, that means the amount of ammonia decreases, that the percent mass by ammonia, and I want to make sure I'm clear on this. So what we saw in the previous slide, okay, is that we have the percent mass of ammonia is going to decrease. So as the temperature increases, we see then a drop, a decrease in the percent of ammonia produced, okay, which means then that means we have less product. We notice here the equilibrium constant changes. The equilibrium constant, not only do we see a change in the equilibrium position, we're going to see also a change in the equilibrium constant itself, and we see that right here. What does that mean then for us? It means then that the reactants, as the equilibrium constant, as the temperature increases, we're going to see then that the reactants become more favored. Okay, so we are changing the equilibrium constant. We are changing the equilibrium constant. We're not adding any new reactants or any new products here. The amount of reactants and products are set. We start this reaction. and we add a certain amount of nitrogen, we add a certain amount of hydrogen. We may or may not add any ammonia, but we add less of it. And so the amount of nitrogen, hydrogen, and ammonia stays constant. Okay, what we're changing here is the temperature. And what we notice here is that a change in temperature results in a change in the equilibrium. What we see happening then is that the reactants start to get favored. We get less and less ammonia being produced. The percentages of ammonia being produced is smaller and smaller. Okay. The reason for this then is because as the temperature increases, we are changing the equilibrium constant. We're changing the nature of the equilibrium itself. The equilibrium now starts to shift more and more towards reactants. It starts to favor reactants more. So that, so we notice here at 35 degrees Celsius, the equilibrium constant is huge, which means then we have then a large amount of product being formed. Okay, so at 35 degrees Celsius, a little bit above room temperature, okay, we have the equilibrium constant highly favoring the product. Look, huge equilibrium constant right here. And that's what I want to draw your attention to. So you have a very big equilibrium constant here, okay, well above 1 million, well above 10 to the 6th. This is 10 to the 7th. This is 225 million for your equilibrium constant here. And then you compare that to the temperature here, okay, at 600 degrees Celsius. This is well below 1. Okay, this is 1/1,000,000th. If this is this is 10 million, on the order of 10 million. This is 1/1,000,000th. So we see this huge shift as a result of the change in temperature. So as we increase the temperature, then we are favoring the reactants more. The equilibrium is favoring the reactant side more than the product side. Okay, so like I told you then, like I pointed out, then why not run the reaction at an extremely low temperature? The answer for that then is that the reaction will be favored, the products will be favored. It's just the reaction runs extremely slowly. It runs extremely slowly. That's why then we got to find that middle ground between temperature, increasing the temperature, and also the yield that we have for the product here. Okay, all right. So with that said, then, if we work this out, okay, I'll go ahead and save this for you as well. Okay. All right. So if we take a look at what's happening here, okay, so the idea behind the shot. Oops, sorry, guys, sorry about this. Whoops. Sorry. Okay. So with Le Chatelier's principle, the idea behind this is then whenever there is some alteration, some change to the equilibrium of a system, okay, whatever that system may be, the system itself will make any changes it needs to in order to reestablish equilibrium itself. Okay, that's what we got. Well, that's what we see here. So using the Haber process again, let's go ahead and let's take a look at this. Okay, so we have then, and let me go ahead and change a little bit here. Okay. So if we take a look at this here, let's take a look at this in terms of the temperature first. We've been focusing on the temperature. Okay, so let's take a look at it in terms of temperature first. I'm sorry, the board is really acting up again today. Okay. Yes, the board's acting up quite a bit. Okay, so, and this will be 2 here. So if we take a look at this, and what we want to be able to do is that if temperature is a factor, if temperature is a factor in this reaction here, temperature basically is a measure of heat. So temperature is a measure of heat. And so with that said, then heat then will play a key role in determining then the direction in which this reaction will take. Okay, so when we increase the temperature, understand this, as we increase the temperature, what we're doing is we're increasing the amount of heat on this particular reaction. We're increasing the amount of heat in this reaction. Okay, so if that is the case, okay, what we can do then is we can consider heat then as a reactant or a product. Okay, either the heat will be a reactant or product. That means that if heat is a reactant, okay, and let me go ahead and write this down. If we consider heat as a reactant, what does that mean then? That means then that we have to add heat in order for this reaction to run. Okay, so that means we have to add heat for this reaction to run. So if heat is a reactant, we consider that then an we talked about this already, an endothermic process. Endothermic process, which means then you have to add heat. Okay? So heat has to be added. And remember, endothermic process means heat has to be added in. And for this reaction run. That means then heat will appear as a reactant. Okay? Now, if heat appears as a product, and we will talk much more about this as we move forward with this. If heat appears as a product, this was referred to then as an exothermic process. And we talked about this as well earlier. Okay? So this is an exothermic process, which means heat is released. Okay? All right. So let's make sure we understand what this means. So an endothermic process, then heat has to be added in. Remember, we measured heat then, we talked about heat then in terms of enthalpy, okay? And so therefore then we will add, for this here, we will have to add in heat. And remember, when we talked about enthalpy, we talked about the change in enthalpy rather than enthalpy itself. So this term here means then a change in enthalpy. So please review these terms here, okay, if you don't remember. So that's going to be, we're going to have to add, it's going to increase in the change in enthalpy, that it's going to go up. Okay? So that's if you have then an endothermic process. For an exothermic process, the reverse is going to be true. We're going to have a loss, we're going to lose, we're going to give off heat. So it's we're going to see a reduction in the change in enthalpy. And so that's what you will look for, okay, when you do this. Okay. All right. So we looked at the Haber process then, and we saw then, and let's consider what happens with what happened with the equilibrium here. As we increase the temperature, we saw a reduction in the amount of ammonia here. Okay. As we increase the temperature, remember, as we increase the temperature, we saw a reduction in the amount of ammonia. What does that mean then? Okay, what does that mean then in terms of where we can place heat then? Now, remember, the Le Chatelier's principle tells us this. The equilibrium will, the system itself will reestablish equilibrium if there's a change in the system itself, okay? Which means then, let's consider this. If we added heat, if this process here was an endothermic process, if this was an endothermic process, okay, heat then is going to be a reactant. Okay, that means then heat will appear on the left-hand side. If this process is an endothermic process, I hope everyone sees this, heat will then appear on the left-hand side. So if we increase the temperature, does everyone see then, if we increase the temperature, then the reaction will shift towards the right, which means that we would have produced more ammonia, not less ammonia. Okay, remember, as we increase the temperature from the previous two slides, we saw then that as we increase the temperature, we got less ammonia, not more. If this reaction, if the Haber process were an endothermic process, if it were an endothermic process, heat will appear as a reactant. And if heat is a reactant, if we increase the temperature here, what we should see then is an increase in ammonia, not a decrease. So therefore, the Haber process here is not an endothermic process. It's not an endothermic process. It is not a process where heat is a reactant. Rather, if we see this, then what if then heat were a product? That is, what if the Haber process was an exothermic reaction? That means it gives off heat. It gives off heat. Heat is a product here. As we add more heat, that means as we turn up the temperature, as we increase the temperature, we're adding more heat. Hopefully you can see then we're increasing the amount of heat on the right-hand side here. What does that mean then? The reaction will shift back towards the left. We will have more reactants and less product. And so what we can conclude here then from the data that we were given, then we can conclude then that the Haber process is an exothermic process. That is, it is a process that gives off heat. That's how we can use the equilibrium here to make that determination. Okay, so our conclusion then, based on what we can observe here, based on our observation here, what we can conclude then is that the Haber process is an exothermic process, which means heat appears as a reactant, heat appears as a product, and that it is an exothermic process. It will give off heat. The Haber process will give off heat as it increases, as it runs. Okay? It is a heat-producing reaction. That's what we conclude from this. Okay, and so therefore, if we add heat, if we increase the temperature, that's why the reaction shifts back towards the left. We form less ammonia because this reaction already generates heat. It already generates heat, so if we're going to add heat, that means if we turn up the temperature on this, it doesn't favor the production of ammonia. It actually favors the production of nitrogen and hydrogen instead. Okay. All right. Okay, so that's how we can use that information to determine this. Okay. Let's take a look at then the next thing. So using the Haber process again. Okay, so let me go ahead and erase this really quickly. Using the Haber process, and we also saw then that the increase in pressure. Okay, so we saw then that there's an increase in pressure that will also affect the equilibrium. And how can we use that to determine, to interpret this reaction here? Okay. All right, so let me go ahead then, and I'm going to write in the information that we know already. Let me erase this really quickly. Let's write down the information that we know already. So based on our data there, we know then that this reaction, okay, this reaction is an exothermic process, okay, which means then delta H for this reaction will be negative, sorry. Delta H for this reaction will be negative. All right. So that's the new piece of information that we have right there based on the equilibrium. Okay. All right. What about pressure? Okay. And how does pressure affect? How do we interpret that? Okay. We saw then. Let's take a look at this. We saw then in this particular reaction that as pressure was increased, as we increase the pressure. I'm sorry. Let me go ahead and do something here really quickly, you guys. Sorry. I'm gonna undo all this real quick. I forgot to do something. Okay. Let me go back to that previous screen. Sorry, guys. I'm gonna go ahead and do undo my, because I forgot to save. Now start over. I forgot to save this screen. I want to make sure you have this. Sorry, you guys. I don't know any fast way to capture, redo all this work here. Now I'm gonna save this screen for you, because you need to be able to make the connection between the heat, the endothermic nature, the exothermic nature of a process, and how we can interpret that, use equilibrium to interpret that as well. Okay, so let me go ahead and redo all this here. All right, you guys. Okay. Okay. Let me save this so that you can have it. Let me go ahead. Almost done here, you guys. So, and then I'll start over. Okay, there it is. So I want to save this right here for you. So I have that. Let me clear everything out here, and then let's talk about then pressure. Okay, so let's talk about pressure, and let me go ahead and write this in again. So how does pressure, and I'm going to include the new information that we have here in regards to the Haber process. Let me go ahead and change this down to 14. All right, so we know then that when nitrogen as a gas and hydrogen as a gas get together, we're going to form ammonia. Okay. Also as a gas. And I want to make sure that you are clear the reason why I'm emphasizing this as a gas here. And we, because this is the pressure is going to affect us. Okay. All right. So with that said then, we also found, because of our analysis of the equilibrium, that the heat, the energetic nature of this reaction is one in which it is an exothermic, therefore it's going to give off. So this is an exothermic reaction. Okay. All right. So how does pressure affect it? Well, let's consider what we had, what we saw and what we observed. We observed then that as the pressure increases, okay, as we increase the pressure, and this is our observation, as the pressure goes up, okay, as we increase the pressure, okay, we saw a result. The result of that is that we saw an increase in the amount of ammonia, increase in the percentage of ammonia that was going to be produced. Okay. Now, understand this, if we can kind of interpret this in the same way that we interpreted temperature, okay, that means then that as we increase the amount of ammonia here, hopefully you're going to see what happens to Kp. Okay. Now, remember, Kp then is going to be product over reactants. I hope you see then that we're going to see an increase in the value of Kp. That means the equilibrium constant will change. This is the opposite of what we saw with the temperature. Okay, so remember with the temperature, as we increase the temperature, we saw a drop in Kp. Here, we expect then that as the pressure increases, the amount of ammonia increases. The reason why Kp is going to increase, remember then, just do the equilibrium constant, the law of mass action for this then. You're going to see an increase in the amount of in the numerator. Therefore, you're going to see an increase in Kp. What does that mean then as an increase in Kp? That means then that at equilibrium, as we increase the pressure, the equilibrium now will favor the products. Okay? Equilibrium will favor products. Equilibrium will favor products as we increase the pressure. Okay, that means we produce more and more. Now, remember, we got to keep temperature constant here, okay, in order to make this examination. But we saw this happen here where we increase the pressure, ammonia, we produce more ammonia. As a result, then the Kp is going to change, that's going to go up, and therefore equilibrium, as we increase the pressure, it's going to favor the production of ammonia. Okay. The easiest way that we can understand how to apply Le Chatelier's principle to this is to understand then that as you increase the pressure, there has to be an outlet. There has to be a shift in order to accommodate that pressure change. Okay, so just think about when you squeeze a balloon. Okay, think about when you squeeze a balloon. Where you squeeze the balloon, what happens then is the gas in the balloon is going to shift to other parts of the balloon. Obviously before it pops, it's going to shift to other parts of the balloon to make up for that part that you apply the pressure on. So if you apply the pressure to one part of the balloon, so you squeeze one end of the balloon, the other side of the balloon is going to increase in its volume. It's going to increase in its volume in order for it to make up for that increase in pressure where you applied it. Okay, this is a concept that we learned a little bit more about in physics. Okay, we talked about it in physics. We refer to it as Archimedes' principle. Part of it is explained through Archimedes' principle, but we learned about that in physics. But you see it in real life. That means if you apply pressure to one end of a system, that pressure is going to shift to other sides of the system, other parts of the system as well, and that's what we have here. Okay, so you can imagine then what happens here. If we increase the pressure, okay, you can imagine that we are squeezing this system here. And as we squeeze the system here, it's going to try to make up for that increase in pressure by reducing the pressure by producing less particles. Okay, so if you notice here, we have 3 particles on the left-hand side. We have 3 particles on the reactant side. So the total number of particles is 3. So we have 3 particles and we're counting all of them here. So we have 3 hydrogens and 1 nitrogen. We have 3 total particles on the left-hand side. Okay, and we have 2 particles on the right-hand side. So if you take a look at this here, we have 3 particles on the left, 2 particles on the right. Good. Okay. So obviously then, if you have a situation where we have 3 particles occupying space versus 2 particles occupying a space, the way then that you can reduce the pressure is by having less particles. So what this reaction will do then is it will shift towards the right. It will shift towards the product, because in this case, then we have less particles on the product side. This will not always be the case. Make sure you understand this. This will not always be the case. Sometimes you will have less particles on the left-hand side. But the idea here then is that when you the reaction, the equilibrium will always favor when you increase the pressure, the side then that will have less particles. That's why for the Haber process, okay, the side that has less particles is the product side. The side that has more particles is the reactant side. So as you increase the pressure, the reaction is going to shift towards the right-hand side to produce more ammonia in order to reduce the pressure. And again, it can reduce the pressure because you have less particles. Okay? And so the way that I like you to try to imagine this then is that in the beginning, so let's go ahead and let's take a look at our system here. Okay, in the beginning, we have then three particles. In the beginning, we have three particles occupying the space here. We have three particles occupy. I'm sorry, four particles. That's why I need to go live with you guys. I need you guys to keep me honest because you have three hydrogens and one nitrogen. We have four particles on the right-hand side. So we have our three hydrogens here and our one nitrogen. So let's go ahead and change this really quickly. Okay, so there it is. So we have then four total particles. Okay. So as we squeeze this balloon here, what has to happen in order for the system to account for that increase in pressure? Okay, come on. Sorry. What the system has to do then is it has to reduce the pressure somehow. It has to reduce the pressure somehow. And what it does then, okay, and so imagine, again, you're going to squeeze this balloon here. What you can imagine happening then is that the system then will produce less particles. Now, granted, the particles here are different, okay, but it will produce less particles, and the particles then will be the ammonia particles, and you only have, and let me draw a different compound. But now you only have two. Four particles will exert more pressure than two particles. Okay, so the idea behind here then is that as you increase the pressure on the system, on the reaction here, okay, it will produce more of the product here. Why? Because it's going to try to reduce the pressure. And that is how pressure affects then equilibrium. And again, if you notice here, you guys, we're not doing any numbers here. There's no calculations involved in this. This is all just qualitatively analyzing equilibrium. Okay, so we see then temperature affecting equilibrium, the constant here. Okay, we see pressure affecting equilibrium, the equilibrium constant. So here, what we're seeing then is we're seeing a change in the equilibrium as a result of a change in equilibrium constant. But we saw then that we can also, there's one other way that we can change that equilibrium can be shifted, okay? And that is by changing the amount, changing the amount of products and reactants as well. Okay, so let me go ahead and save this here really quickly. And let's go ahead and let's take a look at that last scenario there, which is the easiest of the three to understand. Okay. All right. So looking at the Haber process again. Okay. Gas plus hydrogen, gas, okay, producing ammonia, gas. Okay. All right. You can imagine what happens here. If we keep temperature, and in this case then, to make this analysis work, we need to make sure temperature and pressure is constant. Sorry. So we have to make sure those two variables are constant. Okay, is constant. This board is really acting up. Sorry, you guys. It's constant. Meaning then temperature and pressure does not change. Okay, so if that's the case, then hopefully you notice then as if we increase either the amount of reactants or products, that means then as we increase the amount of reactants, okay, the reaction equilibrium see a reaction, not the reaction shifting left. And we see a shift, to the right. To the right to reestablish equilibrium. Okay? All right. If we notice here, if we increase the amount of product, we're going to see a shift to the left to reestablish equilibrium. Okay, and so you can see the inverse will also be true. That is, if we reduce the amount of reactants, here, we're going to see the reaction shift towards the left. If we reduce the amount of product, we're going to see the reaction shift towards the right. Okay, and maybe I should just show it and write that in as well. Okay, so if we see a reduction in the amount of reactants, okay, we're going to see a shift to the left. Okay, and if we see a reduction in the amount of product, okay, we're going to see a shift to the right. Okay, so let me go ahead and clean these up really quickly, you guys, because it doesn't look good for me. Sorry. Okay, so increase in the amount of product is going to shift to the left. Okay, reduction in the amount of reactants, that will also shift things to the left. Okay. So changing the amount of reactants to products will shift the equilibrium. But remember, and this is key here, the equilibrium constant will not change. Okay, equilibrium for all of this here, for all of what we've summarized here, we're shifting the equilibrium position. Okay. So this summary here, so make sure you're able to do this. Okay. So for all this said, but what you want to make sure you keep in mind then is that the equilibrium constant will not change. For these conditions here. Will not change. Okay. Okay. Equilibrium constant changes with temperature and pressure. Okay. But equilibrium constant will not change with the amounts of the reactants or products. That is the concentrations or the pressures. Okay. All right. So make sure you keep that in mind as we finish this up. Okay. All right. Something really quickly. Sorry here. Okay, so the next couple of slides here, we'll just summarize and we'll finish up with the summary here of the of what we talked about. I know it's been fairly long, but these are some of the ways that we can affect the system itself. With the very first one, which is what we ended up with just a moment ago, and that is if we change the concentration, that is changing the amount. And make sure you understand this. This refers to the amount of reactants product. So this could be concentration or pressures as well. Okay, so if we change the amount of reactant or amount of reactant to product, the equilibrium, the system will change. The equilibrium constant will not change. The equilibrium constant will not change, but the reaction, the system itself will shift to the left, that is towards the reactants, or to the right, that is towards product, in order to reestablish equilibrium. And again, changing the concentration here will not affect the equilibrium constant. It will, oh, come on, forward. It will not affect. Okay, so will not affect the equilibrium constant. Okay, all right. So with that said, then, what does affect the equilibrium constant? Changes in pressure, changes in temperature. Okay, so change in the amount of reactant product will not affect the equilibrium constant, but changing temperature or changing pressure will. Okay, and so we talked about this. If the reaction is endothermic, energy can be considered a reactant. Okay, and remember, endothermicity means then that we are adding. We're going to add heat, which is represented by a positive delta H. I'm going to go and write this down. Positive delta H. Okay, delta H then will be a positive value. Okay, exothermic means that we can consider energy being produced. Energy is a product. Therefore, delta H will be then a negative value, and you will have to be able to read that. So you will be given an enthalpy, a change in enthalpy for a particular reaction. Given that value, you have to be able to determine whether the reaction is an endothermic or an exothermic reaction. Based on that, place heat as a reactant or a product, and then use the Le Chatelier's principle to determine then what happens when the temperature changes. Okay. All right, and so the K will change. K, and again, I want to emphasize this here, that the reaction here, that for when you change the temperature, K will change with temperature. The equilibrium constant will change as you change the temperature. Okay. All right, and so with that said, let me go ahead and finish up with pressure here. Okay, and with pressure then, and I'm running low on time here, so what I'll do then is tomorrow's lecture, what I'll do is I'll quickly summarize this. The pressure then is a little bit more difficult to understand. It will shift the reaction towards the left or towards the right because it wants to alleviate, the system wants to alleviate that increase in pressure. Okay? And it does so by favoring the side of the reaction that has less particles. And that's what you need to keep in mind. I want to start with this tomorrow. And I want to finish up with this discussion of pressure, because then it will also give us an opportunity to talk about how entropy, and so we talked about enthalpy already in terms of temperature. We'll talk about how entropy will also be factored into our discussion of equilibrium as well. So we'll pick up with this discussion tomorrow, you guys. I know that there's a lot of talking in this particular lecture here, but tomorrow we're going to apply what we know here to some problems, and we're going to practice applying the Chatier's principle, which is a qualitative assessment of equilibrium without any numbers. Okay, all right, very good, folks, and hopefully watch the video, finish it, and then hopefully I will see you folks. Again, you can type your questions in. Email me your questions, or just write them down. Don't forget them. Write them down, and then you ask when we meet again at the beginning of the new semester. Okay. All right. I'll talk to you guys, or I'll see you folks tomorrow on video. Okay. I'll see you.